Good afternoon, sir.
Good afternoon.
Hope you are doing good, sir.
Yeah, I'm fine. May I know who is on the line?
Subin author this side.
Subin Mathur. Yes, Subin Mathur. Yeah, I have got a couple of emails from you, and I have got the note that you have shared in your yeah. So you have three queries. First query is that in lecture 32, second term of the rate kinetics is not used. The equation is not used. Actually, for that I have to go to lecture 32. Okay, fine. I will just go and just check once what it was. Because I completely forgot what
So
it
you can
was.
directly jump to timeline at 24 minutes. You will see that
No,
there's
I
a
understand, but for that I have to first I have to go to the uh, lecture 32, right? Lecture 32. So it is case study isobutene production, right?
Yes, sir.
Okay. So it is, as you said, it is timeline.
Around
What is that?
24, around 24 minutes something.
24 minutes. Okay.
In Aspen Plus. So just go to Aspen Plus window. So for term 1, when it is equal to 1, then A is equal to 0, B is equal to 0, C is equal to 0, and D is equal to 0. So for all of them, we will have 0. So K1, the term 1 is equal to 1. And term 2, as we have calculated just now, it will be 13.9978, and B will be minus 950204. Okay, so just see, it has come in this fashion. So K2 is equal to 1.2 into 10 to the power 6.
Okay, Subin, exactly what is your query? I forgot. You said that I didn't use something.
Yes, actually, you'll see that there are two terms in the nominator side. So for the second reaction constant, that was not used. So only the first constant parameters are used.
First constant parameter was 13 point something something, and second parameter was 950204, right?
So the second constant term for the capital K, no, that was not used. Let me just again go to that lecture particularly. I let you know what was the issue. Just a second, just for a second. Yes, sir. The kinetics constant, which is equivalent to 1.4 10 to power 6 e to power minus 117 by RT. That particular constant was not used. Hello.
Yes. Please carry on.
Yes, sir. The second constant term which is equivalent to 1.4 to the power 10 to the power 6 e to the power 117 by RT. This second term is not used actually. There are four constant given. There are four constants given, no? Reaction constants. After that, the value of R is also given in the problem statement.
Right. Huh.
So that
Yes.
second parameter is not used
So
actually.
parameter means capital K. You mean to say capital
K.
K.
Right. Exactly.
Capital K is not used. Okay. Have you seen the way it is given? I mean,
Yes, sir, I have seen this, and I also tried to simulate that particular lecture, and I found that the results were not actually converging. Actually, I was not getting the products.
why I am asking, because you see the value of K over here. It is 8.9, right?
Right, sir.
The first K is 8.9 10 to the 5.
Right, sir.
And if you multiply this, or you mean to if you divide K by capital K,
But still, you will left with a capital K as a multiplication factor for the first term. I understand that we can take the capital K out of the bracket for the second term to be unity 1. But in that case, the first term will have the capital K.
No, what I am saying, that if you consider capital K, it will be a very minute term compared to the one which we already have, isn't it? In one way, you are having K, and the other way, you are having small k by capital K. If you compare these two things, the first term is only K, which is having to the power 5 power.
Right, sir.
And the second term is small k by capital K, which is merely point. I mean, you can see the number. It's almost 1.
I understand.
So where it is 1 10 to the power 5. So it may be neglected. That is my understanding. I mean, I right now I forgot exactly how I have derived, but probably I have forgotten to mention, or that's how I arrived at that decision when I created the case study. But with a hindsight, probably that is what I have seen, and then I didn't include. Maybe. Have you included those terms and got a entirely different scenario? I mean,
Yes. Actually, sir, I tried. Actually, I followed some other videos on YouTube, and I found that there is a method to introduce two terms when there are two terms in the nominator side. So for that, you have to enter K value equal to 1 and E value equal to 0 in the that reaction context window, and in the driving force.
I didn't get you. Sorry.
So there's a window there in the reaction kinetics when you enter the reaction kinetics parameter for K and E.
Huh.
So when you have the two terms in the nominator side, you put K equal to 1 and E equal to 0, so that later in the driving force section, you can put the term 1 and term 2 in the ln form.
No. I mean, I understand there are methods to insert two terms. I'm not challenging that. What I'm asking, have you included both the terms and got a result which is very, very different from
Yes, sir. Actually,
whatever?
I tried to enter both the terms, and I found that the reaction is not giving actually butene and hydrogen.
It is not giving the it is not giving butene and hydrogen.
Yes.
then I will explore it because it should give. I mean, in my understanding, there should not be much difference. But as you are claiming that, I will definitely explore. I mean,
I
I will.
can share you my simulation file
Uh,
separately if you want.
please, 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 please.
Sure, sir. Sure, I will definitely share, and I have already shared one simulation file with you. That was for lecture number 29, if you
Uh,
remember.
yeah. I mean, okay. Lecture number 20. Subin, right? Okay.
Yes, sir.
Ha 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 ha. Right, right. I already answered you because I have seen your simulation file and I couldn't understand why it is not functioning. I mean, I'm sorry. I mean,
So,
I couldn't
so
go
that was
beyond.
lecture number 29, and the similar thing is actually happening with lecture number 32. And by tomorrow evening, sorry, today evening, I will share the simulation file of lecture number 32. The way I have entered the parameters.
Okay. Okay. Yeah. Sure. Okay. So yeah. So that is the first thing that you have mentioned, Subin. The next thing that you have mentioned about question number 3 of assignment 9. Yeah,
Yes.
I understand that is the wrong format of the question because decanter 2 and decanter there are two decanters and I have asked for only one answer and the question format was not proper.
Okay.
So I have to drop the question. I have already mentioned it. I
Mhm.
mean, I have told it to the NPTEL authority to drop that particular question. Okay,
Fine, sir. Fine.
because right
Mhm.
now I cannot reformat and float it.
Understand, sir. Understand.
So that will not be null and void, that question.
Fine, sir.
And third one, you are asking in Aspen Plus, can we design vessels and separators like it is LD manhole? No, 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 no. Those things cannot be designed that way.
Mhm.
The column internals can be designed, but to some extent they will be trial and error. I will show you an example. Um, just 1 minute. I will. Mm, okay. Um, for instance, 1 minute.
So meanwhile, can I ask one more question?
Just let me explain this first, okay?
Sure. Sure, sir.
Otherwise, I'll be out of the flow.
Sure, sir.
Okay. Okay. So, are you able to see my screen?
Yes, sir, it is visible.
Okay. So you can, I just make one quick run. So basically it's an absorber stripper combination
Yes, sir.
where CO2 is being fed through the raw feed and lean amine is being passed through it, and in the absorber CO2 is being absorbed by lean amine and the rich amine is going, and here the stripper with the stripper the CO2 is being released
Right, sir.
and the lean amine is being recycled back into the system and this absorber. So here you can see the CO2 per kg, it's kg per second is 69.69 kg per second of raw feed is being fed to the absorber. Only 3.45 kg per second is being, it's there in the absorber, but the remaining 66.19 kg per second, you can see the mass flow rate of this gas is 70.81 kg per second, out of which 66.19 kg per second is only CO2. So basically this is a CO2 sequestration process where we are trying to concentrate CO2 and then we are the later part, the downstream part of this is not shown, but we will compress the CO2 and store somewhere, etc. Why I have opened this file to you? Because I wanted to show you the column internals, as you have asked whether we can design L and D. And you can see the flow rate of the amine, lean amine and flow rate of gas. In terms of kg per second itself, it is, it is
Quite.
1,000, quite large. So here in the blocks, if you see absorber block, there is something called column internals. In
Right,
the
sir.
column internals, I have a section. This is so actually I have a section of I will show you first this. The section I have 31 to 30 stages, number of stages, and I have specified whether this will be a packed column or tray column. I have chosen packed column. The mode will be rating or interactive sizing. I have chosen rating. Then the packing type, Raschi ring or Paul ring or Melapack or so many things are there. I have chosen Melapack.
These are standard types of packing.
These are the standard packing, and standard packing and the vendors of the standard packing also can be chosen. Sorry. And then material is standard or plastic. The dimension, these are all standard dimension. Each and every dimension has a meaning. Or 250y has a meaning, 250x is a meaning, has a meaning. And you can see the diameter.
Right, sir.
Diameter is 24.5 meter. So you can imagine what a
Large it is.
gigantic size it has. And the trace spacing, you can see that actually it is an entire column. So it is 40-meter column. So 40 meter by 24.5. So L by D ratio, we are maintaining around this, but diameter, you can see what is the diameter. And if you want to view the internal summary, then you can just press it, and there you can check. So it is a 30 number of trays, total height 40, total head loss is is meter. If you want to see it in PSI, maybe maybe you will be able to. I don't know how is PSI or millimeter. If you say it is 691 millimeter, I don't know whether it will be accepted as per the norm that you follow in your industry. But that's how it is. Total pressure drop will be in millimeter, it will millibar, it will be 68 millibar. I believe it is within the limit. And then this is the diameter section height, and here you can view. If you view the sections, then these are the okay, not this one. I wanted to show you something else. Oh, geometry. Yeah. Here you will find geometry. Okay. So it is a stage-wise size. This is what I wanted to show. No. Sorry. All those WhatsApp messages are floating. Somewhere the size will be
So
shown.
in previous lectures, you have actually already taught us how we can size the column internals.
I
I've
did.
seen, yes, sir, you have.
Okay. I prepared this the lectures a couple of years back, so I almost forgot. Anyway, the hydraulic plots that you can use.
It is there in the lecture. We can see the hydraulic plot and the column internals as well.
Yeah. So that much we can do. That much we can do.
Right.
More than
So,
that,
but in this particular case, I could see that the diameter of the column is quite high. That is actually 24.5 meters is actually impractical, seems impractical. So, for these types of problems, okay, do we have actually a number of columns in series, or how we,
yeah, obviously, if the flow rate is so high, so if you feel that it is impractical, I mean, up to 30 it is allowed, I believe. I mean, they said that up to 30 it is allowed, 30-meter diameter it is allowed. But if you feel that it's very difficult to manage, then you have to divide it in 2 or 3 columns, and you have to do it parallelly. Maybe 500 kg per second per column. Okay.
Right.
How you can do. Okay. That is one thing. So this is about Subin. Okay, now I find another question by Mr. Pranav Sinde. Okay, I have Ashish over here. So Ashish Sharma, are you here?
Yeah, good afternoon, sir.
Ashish. Okay, I have got your question, and I have got your assignment 10 also. In part B of assignment 10, answers are not matching. I am sharing the APJ file. Kindly check that what has been done wrong. Okay. I do not know whether I will be able to find what is done wrong, but I will definitely check it. Just a minute. Let me open your file. Oh, somehow it is not, your file is not loading, Ashish. Meanwhile, let me answer Pranav Sinne. Pranav, are you here?
So Pranav is not there, but I was facing the same issue. The same issue the Pranav has mentioned.
Okay, so this is about the same assignment 10. Yeah, okay.
Yes, sir.
Assignment 10 is again, this is LH, HW type of problem, right? Which I was discussing you in the very beginning of the session, right?
Right, sir.
So it's the same problem. Now I wanted to open Ashish's file. It is not opening. But I will show my file that I have done. So, so this is the PFR we were talking about, and just 1 minute. I will first check it. Where is that file? Okay, so this is the file that I have got, which I prepared during my.
Sir, I too have shared my file with you.
Okay, let us. So this is Ashish's file, I believe.
Okay.
Is it Ashish?
Yes, sir. This is my file.
Okay. Okay. Let us check this one. Okay, Subin, I will check yours later. So probably the other parts are okay. Feed. I don't know. Feed. There won't be any problem with feed. I believe feed is.
Sir, I think the problem lies within the LHHW kinetics.
Right. So. Uh, 20 methane, 40 oxygen, 160 nitrogen, and 10 water. Okay. So PFR, okay, PFR. PFR is 5 meter and 1.5 meter configuration, and reactor specified temperature 500 only. Okay. And then catalyst 1000 kg, 1000 kg, yeah, 1000 kg, and 0.35 bed voidage. Okay. And you have specified the reaction. Check the reaction first. Okay. Okay. So reaction kinetics, it is so CH4 plus 2O2 is equal to CO2 2H2O, right? Then it is 1810, 72.6 vapor phase, molarity catalyst. Exponent 1 fine. Okay. Then okay. And then you go to absorption part. No. Adsorption is second part, right? H2 is the term 2, not term 1. Term 1, term 2. So term 1. Yeah, that's okay. That's okay. But why you have not given the second term? You already have CO2 over here, right? So you have to include CO2, isn't it? Why you didn't give?
So we don't have the second term. I mean, we don't have the CO2 in the consideration in the second term. We only have the water.
But then
In
it
the
is
absorption
0,
term, no?
0, right? I think you have to give 0, 0 for that. Let me check. Vapor molarity catalyst. Basically, you have to give everything except the water where the term 2 will have 1. But you have to mention everything, I believe. Term 2 will be this. Okay. Here I have done a mistake. Actually, it is minus this, no? So it should be minus. Okay.
Yes, sir.
This should be minus.
Minus.
Yes, sir.
Yeah.
And the second term B constant should be minus 2.8987 because the R is given in that format, no? Sorry.
I didn't get you. Sorry. This is the format.
So the value of A is correct.
The value
The
of A
only
is correct.
mistake was negative sign. Only
Huh.
mistake was the negative sign in the value of B.
Negative sign, right. It
Yes,
should be negative sign.
A is fine.
A is fine, the B should be negative, right?
Yes,
But
sir.
yeah, this is my file. I just but this was is yours, right?
Yes, sir.
And okay, you have given it right. So whatever you are getting, I believe you should be able to run it properly. Okay. Yeah. So I'll do one thing. I will reevaluate the thing and I'll update the answers. Okay. Thank you for pointing out. Mistakes happens. I have
Okay,
done a
sir.
small mistake.
Thank you, sir.
Okay. Anyway, I will update the assignment 10 answers according to minus sign in that. Okay.
Okay,
Fine,
sir.
sir.
Sure. Fine.
Great. Okay.
So, it,
So, yeah, Subin.
yes, sir. In one of the lectures, you have mentioned that
What,
the reaction
Subin,
chemistry.
I will check whether some people are waiting in YouTube.
Okay.
Okay, YouTube, not many persons are there. Only one person is there. Dharmin Shah is saying, when will hall tickets be out? Dharmin, these questions will be answered. I mean, you just go to that particular forum. They will answer these questions because these are not handled by me. You know, I mean, hall tickets, when the hall tickets will be out and all. Separate NPTEL section, and they will tell you in the forum. So you just ask me questions about the content and the lectures. Okay, I can answer them. Yeah, Subin, you were asking me something.
So, in one of the lectures, you have mentioned reaction chemistry. So, I wanted to know why reaction chemistry is different for property setup and simulation setup.
Which one?
It's
Can
it's
you?
uh, it's about the lecture number 31. There were some ions involved.
Ah, okay. I okay. Did I close that particular simulation? Let me check. No, I probably not. Okay, I will open.
Hydroalkylation of toluene. It is.
I understand. Okay. Uh, for instance, I will show you some other. 1 minute. Okay, is it visible? My screen?
Yes, sir.
Yes,
It
sir.
is
Visual.
visible.
Okay. So this is another CO2 sequestration model that I have done. Only difference is in the earlier case it was with MEA, monoethylamine, and here it is with K2CO3. Okay, K2CO3 and piperazine. So you can see that we have a set of reactions for K2CO3 piperazine that may work with uh, react with CO2. Some of them are equilibrium reactions and some of them are kinetic equations. And the kinetic equations they have their kinetic parameters written. Equilibrium reactions, they have their equilibrium parameters written. But there are some additional, but most of them are, they are equilibrium equilibrium by nature, because even the, if you see PzCO2H2O, they are producing PzCO minus plus H3O plus. But the second kinetic reaction I am writing PzCO minus plus H3O plus, it goes to PzCO2H2O. So effectively all of them are somewhat reversible kind of reactions. But there are certain reactions where they are not reversible. Once it is a kind of dissociation, salt dissociation kind of reaction. They are not given over here. I mean, if you say new, if you place new over here, it will ask for kinetic, equilibrium, conversion, and salt precipitation. But salt dissociation reaction is not available. So what we do, we go to properties and then in the properties, we place chemistry. In the chemistry, we place those dissociation reaction. For instance, we use K2CO3 and KHCO3, which dissociates into the ions of potassium and carbonate and bicarbonate. And KOH dissociates into potassium and hydroxyl ion. Okay, and these dissociation reactions cannot be given in the reaction kinetics over there. So we specify them in properties. I mean, that's how the Aspen Plus has been designed. Okay, so there we place it, okay, in chemistry, and rest of the section, rest of the thing we can place it in equilibrium, in reaction kinetics. For instance, if you say new, okay, new, it will ask for whether it is an equilibrium reaction, whether it is a salt, precipitating salt, and whether it is a dissociation reaction. If it is a dissociation reaction, dissociation of which electrolyte? For instance, here I have chosen KOH electrolyte. Here I have chosen K2CO3. Similarly, you have to choose the particular dissociation and say that, okay, I want this particular chemical to dissociate. Okay, that's how it works. Now Aspen has been so here you don't find any kinetic reaction. Okay, so so Aspen has divided these things into chemistry and reactions. I do not know why they have done it, but so, this is how Aspen has been designed. So I do not have much comment on this.
It's okay, sir. So okay, we would like to. Yes. Okay. Yes, sir. Yes. Yeah. I got your point, sir. So we would love to learn more from you, sir. So can we have, I mean, sessions on lectures, sessions and lectures on Aspen Dynamics and Aspen Plus HYSYS as well, Aspen HYSYS as well, anytime sooner? Yeah, actually, I am planning to prepare the slides, but as you know, it's a gigantic task. And in fact, I am preparing the Aspen Plus advanced version, where the piping design and other things will be there. I mean, the portion which I didn't cover in the first part, the second part will be covered over there. So that I am preparing, but it's too tiring, and I have the approval, but obviously I will float the course in near future, maybe next semester. So to please have some courses on this Aspen Dynamics as well as on Aspen HYSYS.
Yeah, I will definitely do in future. I will definitely do. Okay.
So we will be eagerly waiting for those lectures and learnings.
Okay, sure. Thank you.
Thank you, sir. Thank you very much for your support.
Mhm.
Sir, I have a small question about the catalyst in the reaction.
Yes, Ashish, tell me.
So, in the reaction, we are only defining the amount of catalyst in kg and the void fraction. So, in the question, the name of the catalyst is also defined. So, is there any provision in the Aspen that we can define what catalyst we are using, or we are just with the only the weight and void fraction of the catalyst?
It is only weight and void fraction in the catalyst, because catalyst, what it does, increases the so all the related uh, information of the catalyst, like reaction rate and all, everything you have mentioned over there, right? So in
Yes.
presence of catalyst, the reaction rate is this. In absence of catalyst, the reaction rate will change. Once you have provided those reaction rate information, then you are good. I mean, what is the need of telling whether you are using platinum or gold or whatever? So they
Yes.
are not necessary. No?
Okay, sir, fine.
In YouTube, I do not know how many of them are there in YouTube. YouTube listeners, you may please ask questions, if you please. YouTube listeners. Okay, I don't think there are many listeners in YouTube. So, Subin and Asis, do you have any more questions, or?
So we are done with the questions, sir.
Okay. What about Ashish?
No, sir, I don't have any question right now.
Okay. Okay, NPTEL, then you can end up the session. We do not have much audience over here.
Okay, thank you, sir.
Thank you, sir. Thank you.
Okay, NPTEL, please close the session.